Hello, friends. Welcome to AI A to Z. I'm Dr. Sonali Tamhankar, and today we have AI for the Futurist. Q is for quantum computing. Quantum mechanics is the theory that explains how our world works at tiniest scales. At this level, things behave in ways that completely defy our everyday intuition. For example, imagine throwing a tennis ball at a wall with two narrow windows. You would expect the ball to go through either window 1 or window 2, right? That's common sense in our macroscopic world. Now shrink down to the quantum world. Electrons passing through a wall with two tiny slits don't behave like tennis balls. They create an interference pattern much like water waves. Stranger still, even if you send one electron at a time over many repetitions, the interference pattern still emerges. Somehow, each electron appears to interfere with itself. So, in our daily world, we can either have our cake or we can eat it. In the quantum world, we can be suspended in superposition states with non zero probability of both having our cake and having eaten it too. Or at least that's how we would experience the world if we were electrons. I link a fun book below called Alice in Quantumland. So, this strange behavior is what makes quantum computing possible. Nature is naturally exploring many possibilities at once, something classical computers struggle to do efficiently. So, quantum computers can harness this, allowing them to solve certain problems in ways classical computers can't. Quantum algorithms can exploit this superposition and interference for better parallelism. Another exciting application is quantum simulation. Richard Feynman famously said, if you want to model nature, you would better make it quantum mechanical. Because chemicals, materials, and biological molecules, these are all quantum systems. A quantum computer can model them directly, helping us understand protein folding, designing new materials, or even accelerate drug discovery. So, quantum computers can also be efficient at optimization because a lot of AI algorithms involve minimizing something like an error or loss function. This can be thought of as finding the lowest point in an error landscape. So, just like a ball naturally rolls down a hill to find the lowest point, a quantum system naturally finds its lowest energy state, a fact we can use to solve complex optimization problems. Classical balls can get stuck in small valleys, but a quantum system can tunnel through the hills to find the true lowest point. But here is the catch. Quantum computing is hard in practice. Building stable computers is extremely challenging. Qubits, or the basic units of quantum information, are fragile and prone to errors. Maintaining these pure quantum systems long enough to compute without decoherence is a major engineering feat. Still, the field is progressing fast. IBM now has processors with hundreds or even about 1,000 qubits. Google and IonQ are achieving remarkable control and error correction. Cloud platforms and tools like Amazon Bracket and IBM Qiskit make it easier than ever to learn and experiment with quantum hardware. But hardware is only half the challenge. Coming up with good quantum algorithms is hard too. Quantum computers don't follow classical logic. Superposition and entanglement let qubits explore many possibilities at once, but you need clever algorithms to make the right answer emerge. Only a handful of general purpose algorithms exist, like Shor's for factoring or Grover's for search. So, after decades of steady progress, one could argue that we have now officially entered the quantum age. This is no longer just a laboratory experiment. The industry is scaling rapidly. We are seeing an ecosystem of over 40 distinct quantum processing units. The intellectual property landscape is exploding with over 10,000 patents filed in 2024. And venture capital is fueling the next generation of quantum hardware and software with about $1.6 billion invested in 2024 alone. Now, what does this mean in the real world? So here are three checked milestones where quantum is already making waves. The IonQ and Kipu Quantum broke new performance records for protein folding and optimization problems in 2025. Researchers at the University of Toronto and others are using quantum algorithms paired with AI to accelerate early stages of cancer drug discovery, generating and testing promising candidate molecules in the lab in a matter of months rather than years. In the world of high-stakes trading, quantum-enabled bond trade prediction at HSBC saw 34% in predictive performance. So yet, most of today's computing doesn't happen on quantum computers, and that's unlikely to change soon, but this is a field to watch. Researchers and engineers are exploring deep synergies between AI and quantum computing. AI and machine learning techniques are already being used to help optimize quantum circuits, to calibrate qubits, and enhance error correction. And in return, quantum computing holds the promise to accelerate some of the AI workflows beyond what is feasible with classical systems alone. So here are our quick conclusions for today. This positive feedback loop between different technologies will only accelerate, and we can make use of the fact that the weirdness of quantum mechanics, right? So we have the states in superposition and entanglement. These very weird things give it the advantages for parallelism and optimization and simulation. So quantum computing is a maturing technology. We saw that there are a lot of advantages and advances, and there are emerging real world applications. But this is still relatively early in the field, and the field will keep developing over the next few years and maybe decades. So thank you for joining today. Tomorrow we have the much discussed R is for RAG. We talked about it when we talked about knowledge graphs and some of the other topics, grounding, retrieval augmented generation. So see you tomorrow. Bye.